upload the data again. So we refresh, and my plan for today is let's run this iMod code. And first suggestion, if you really want to learn, you have to do it. So if you follow my presentation and you don't repeat at the PC, it's not enough. So if you really want to learn, when I say bring your PC, I tell you, if you have problems, you don't have a PC, just let me know. I can bring an old PC for you. Okay? It's not really, or I can make an extra effort to find. I'm planning another more lecture with the PC. I can book a lab, or I can bring an extra PC. But if you don't repeat what I'm doing, you know, it's difficult to learn. It's like studying a language without speaking. You don't learn it. Okay, so let me just download the data again. And I think I have almost everything, but let me check. Okay, I think I just need the code. So, just 1 second, I take the code. The code. No, sorry, this is cost engineering. Okay, this is the code. Let me copy it in a... If you remember, we went through this code together, okay? So let's take it for learned, and let's now focus on running it. Just 1 second, I'm saving it in a file. So this is my file with the code. I save it in my desktop. And this is imod.r. And then I increase also the font size, just 1 second. Okay, this is my code, and then I can open an R window. Okay, again, I'm not using RStudio, and I'm just using the console, because this makes also easier for me the presentation, because otherwise it becomes too small, the console. But you are welcome to using, and I suggest you to use RStudio. Okay, now let me upload the data. And the data is, so let me say P equals scan. 1 second. I need to go into the right directory. Okay, so P equals scan, and this is rain, okay, and the skip equal to, just 1 second, while I upload the data, I'm not making many comments because you already know how to do it, and then I need to make it an array. So pi equals array p dim. I make it an array. It's 28760. Okay, and then let me see pi 110. I make a check if everything is fine. Okay. Okay, good. And now I can say P equal pi 1, comma, and P equal pi 2, comma. I can remove pi good. And I make a check just to make sure I plot the plot P, type equal line. I make a check to make sure that everything is fine. Yes, this is precipitation. And let me plot E, evapotranspiration potential. Yeah, it's fine. And then I need the observed data, QOS equals scan. Sorry. Just 1 second, I don't remember this church. Okay, skip, equal to, sorry, equal to, okay, good. And let me plot QOS just to make sure that everything is okay. Type equal line. I have the keyboard on my PC that is not working anymore. I already ordered the new one. Okay, good. So, now if I list my variable, I should have P is rainfall, precipitation, E is evapotranspiration potential, and QOS is the observed data. Now, let me upload now the code of IMOD. So, source, and the name of the code, imod.r, good. And in this way I uploaded the function. If you have any question, just ask me, please, okay? This is the upload of the function, and now if I list the variable, I find also the listed imod, which is a function. If I just type imod, I should get the list of the function, everything good, everything is okay. Now let me go back to the file with the program. Here it is. Because let me change the fonts. So, this is the function that we wrote, and you see that the argument of the function is just a vector, the parameter vector. You remember 5 parameters. We need to, if you want to run this program, we need to give values for these parameters. And here you see what is the meaning of the 5 parameters. So, in this vector, the first element of the vector PAR is Cmax. The second element is beta. The third is alpha, which is a weight, splitting the contribution in quick flow and slow flow. And then there are the Ks. The Ks are the parameters of the reservoirs. For the quick flow, there are 3 reservoirs. For the low flow, there is just 1 reservoir. And do you remember that we noticed that this is not a time, but it's the inverse of a time? So basically, we need to give values here which correspond to reasonable values. And then if we want to run this model, if we want to run this function, we need to specify a parameter vector. And we have to specify reasonable values, because otherwise, if we give values that are not reasonable, first, the simulation is not good. Second, it may happen that it gives an error to the program, because if for some reason the function computes values that are infinite or not defined, then it gives an error. Okay, let's try to run it. And first of all, let me check at the bottom of the function what is the value that is returned, whether there is a plot or not. So, given that now what I want is to try it by trial and error, not automatic. And if I want to try it by a trial and error, it's better that I get back from the function, given that it's just one run each time, it's better that I get back the plot. Because in order to assess the goodness of the simulation, it's better to refer to a plot rather than referring to a value like sum of squares, which is difficult to understand, to interpret. Okay? So let me check whether there is the plot back here, and yeah, there is the plot, and the simulation starts from 1, I check, and also there is the sum square that is returned. Okay, that's fine, provided I have the plot back, I also can accept sum squares. And let me see if the simulation starts from the beginning. No, you see SK is the starting time of the simulation. Let me put here 1. Okay, because I want to start from the beginning of the simulation, the rule here. And then, given that I changed the code, I need to re-upload it. So now I move to R, okay, to the R window. Here it is. No, this is the graph. This is the R window, and I go back with the arrows. I get back the instruction, source instruction, to re-upload the program. Anytime that you change the code, keep it in mind, it's not automatically changing into R. You need to re-upload it. Okay? Okay, good. Before I start, let's save the image, just because, you know, one never knows. Save image. Okay, good. So I saved it. So even if I have a crash, etc., the data are saved. Okay, so let's try to run imod. So imod, and then I need to put the parameter vector here. The argument of the function is a vector. You remember PAR. And here I have to give values for the elements of the vector. So the first element, I said it's Cmax. Okay, Cmax is storage. It's in, if I well remember, it's in millimeters. And a sensible value may be from 50 to 500. Let's try with 200. Okay. Now, second value. The second value is beta. Beta, you remember, varies from 0 to infinity. Okay, let's put 0.5. Okay. Beta equal 1 is linear graph, if you remember the theory. And now alpha. Alpha, okay, let's try with 0.5 again. It splits the surface flow into components. And then there is decay. Okay, decay is a time in our first interpretation of the linear reservoir. And if it is a time, I'm not sure whether I mentioned it to you, a guess value for K intended as a time is the time of concentration of a watershed, which is the timing required by the drop that falls in the furthest, or let's say, in the location that is more distant from the closure to reach the closure. So it's something that for a basin of 1,000 square kilometers, maybe 10 hours. 10 hours means 36,000 seconds. Given that, my guess was that here it's the inverse of a time, let's try to put here 1 divided by something like 20,000, because this is the quick one. But the quick one, I would say, let me put here 10,000. And the other one, let me put 1 divided by 40,000. Okay, let's see what happens. First, the first question is, does it run or not? Let's see. Yeah, the evapotranspiration is EP, not E. So let me write EP equal E, and then remove E. Good. Let me try again. Something is happening. Let's see. Okay, here you get back the sum of squares. Now let's look at the graph. Okay, very bad. It means that the parameters are not good, but still, I mean, we got a simulation. You don't have to be disappointed. Now the big question is, what's wrong here? Of course, we have parameters that we made by guess that are wrong. If you get a simulation that is flat, the red line is the simulation, something is wrong. And now the big question is, what's wrong? So what should I change? And we may move forward in two ways. If we don't have any experience, if we don't have any clue on what's wrong, we may just try. And randomly we change the parameters. Okay, this is one first possibility. And which is reasonable. It takes longer than the second one, usually. The second one is that I get a clue. Like, I understand what is the parameter that may be wrong here. And then if I get a clue, I try to change the parameter in that way. So, how to gain a clue? Again, two ways for getting a clue. The first way is that I go back to the first option, I change the parameter randomly, and when I find the right move, I store it in my memory, my experience, in order to understand what's the effect of a single parameter. So if I move forward randomly, I could say, okay, let me start by changing the first parameter, Cmax. Let me change the storage. And then I see if it is effective. If it is, I store it in my memory to build my experience. But there is a second possible way, like try physical reasoning. And I stimulate you to go along this way. Try physical reasoning. So, if this simulation is too flat, and be careful, what's going here is that starting from the initial value, there is a continuous decrease of river flow. So it seems that the model doesn't get any rainfall. Why is that? So what is the a possible physical explanation? A possible physical explanation is that the model is just storing rainfall into the watershed. It's not delivering it to the outlet. So, if this happens, let's try to reduce storage. So let's try to reduce Cmax. But be careful, we have two storages in this model. We have storage in the form of Cmax in the catchment, and then we have storage into the linear reservoirs that we use to propagate the runoff. So it may be also the storage of the reservoir that is wrong. And what is the situation which brings a linear reservoir to store a lot of water? The situation is when the key value intended as a time is too long. So probably the k values may be wrong here. Let's try one option at once. So let's try with the first, which I don't think it is the correct one, because the first I put a storage was very reasonable. I'm more tempted to think that probably it's the k values that I gave that are not good. Okay, let's try with the storage first. It's very simple to make a try. Let me go back to the R console and let me change it from 200 to 1. Let's see what happens. I don't think, yeah, you see that there is almost no change. There is some change. There is some change because you see that now we have these ups that are more visible, and also in the previous situation we had a decline of the red line. Now it's still declining, but not so much. There is some change, but it's not what matters. It's not that effective. So let's try to change the case. And this is the only possible solution. If you think how this model works, the other parameters, beta and alpha, may not be so effective. So let's change the case. And let me go back to the value 200. So there is something wrong here. And what could be wrong? Let me try, maybe that I misunderstood the fact that k is the inverse of a time. Let's try with timing. I don't think this is the solution, but let's see.